Hey everyone, welcome back. In this lesson, I want to be a little more specific about what it means to be a set and what it means to be a member of a set. Earlier, we looked at the set of real numbers, we looked at some subsets of real numbers, but I really want to discuss um, what a set is. So, first of all, a set is a collection that can have no repeated elements. So, the real numbers are a set because we don't have the same number more than once, right? They have the number 7 and it might appear as a digit in 17, but it's a different number. So it's a real number set, no repeated elements. And sets can be related to each other in many different ways, and we can have operators on sets. So I want to discuss these first. This is read A contained in B. Let me go ahead and bring this over to my paintbrush because I want to be able to kind of draw on this a little bit. So this here is if you look at it, that symbol, it looks like a C, and it's read contained in, okay, or just contained. A is contained in B. All the members of A are also members of B. They're completely contained in, but strictly smaller than. Here, just to demonstrate this is the opposite. B is contained. Again, that symbol is contained, and that's why it's shaped like a C. It kind of looks like A or B is like inserting into A, and it is read B contained in A. All right, let's take a look at this one. This is the same symbol, but now it's pointing upside down, and it is read intersect. So they use this symbol because intersect sounds like it begins with the letter N. You see how that's an N, an upside down kind of lowercase n. And that's because this A intersect B is all of the members that are in both A and B at the same time, where their Venn diagrams intersect. And this is a union B. So look how it looks like a U. It's the same symbol, just rotate a different way. This is pronounced union. So if we union two sets, it's everything. Everything in A that's also in B. But you don't count anything more than once. So if something's in A and B, you only list it one time. All right. We have a little definition here. It says the number of elements in a set is the cardinality of the set. So what that word means is, like, if I have a set of 2, 4, 6, 8, pretty simple set. Well, the cardinality of that set would be 2, 4, 6, 8 is four different members of that set. So the cardinality we would say is 4. All right. Our first example problem is going to be to make a Venn diagram, and then we're going to use it looks like, to answer some questions. So that should be cool. All right, so we're going to draw a Venn diagram to describe the relationship between the following sets. All right, I know you've made Venn diagrams before. Maybe you made them in a social studies class, comparing the different regions of two different countries or different peoples. Well, I I have to mention this. You were doing math because John Venn, the inventor of the Venn diagram, was a mathematician. What was he studying? He was studying sets. John Venn was an algebraist that studied set theory. Now, when I say U, I almost always mean the universal set, okay? So, to really discuss sets, we need to understand what is the universal set. And in math, the universal set is often the real numbers. And then we're looking at smaller subsets of that universal set of the real numbers. But here I'm giving you one, and I'm just giving them, its members are actually these letters, okay? So that's the universal set. That's all of them that we're going to be dealing with, okay? And you can think of the universal set as being this region out here, okay? And so all of these letters have to fit somewhere in this universal set. So set A is A, B, C, D. But you'll notice CD is actually in both sets. So I'm just going to put A and B, and then C and D has to appear in both sets. And then I've got E and H. And I think, so we have A, B, C, D, E. I think we're just missing F and G. So I'm going to put F out here and G out here. So that's our Venn diagram. I'm just going to kind of label it. This gets confusing when you're using letters for members and set names, but I think if I say this is U, and I say this is S, maybe I could do like a double strike S or something, like the double strike R. There's T, huh? That looks good. It's clear which one is which, that's me trying to bold them. Okay, so, and the red letters are the members, and the black is the name of the set. Okay, I think we're ready to answer questions now, aren't we? Okay. And of course, I'm referencing the wrong example number. It says use your Venn diagram from example, well, it should be 4.1 to answer the following questions. So sorry about that little misspelling. All right, what is the set S intersect T? Remember that symbol there means intersect. So S intersect T, and we're going to use set notation. Makes sense, right? We're dealing with sets. So S intersects T, that's C comma D. Looking back at the descriptions of the set, those are the only two members that appear in both. What is the set S union T? That's everything that's in both S and T. Now, I can't just list A, B, C, D, and then list C, D, E, H, because we're not allowed to have repeated elements. So I don't want to list stuff that's in both sets twice. So I'll start with A, B, C, and D, and then I'll just add E and H. And we just separate members of the set with commas. That's all we have to do. All right, what is the complement of S and U? Well, we actually haven't seen that one yet. It's notated a lot of different ways, but oftentimes it's with a tiny little C in the corner for for S complement, C for complement. So using that C symbol a lot. What it means, the complement of S and U, it means everything that is not in S. So the things that are not in S are E, H, F, G. And in fact, oftentimes people will describe the complement as simply not S. So that is, we said what? E, H, F, and G. Which sets is the value D a member of? Which set? So possibly more than one. Well, it's a member of set S. It's a member of set T. It's definitely a member of set U, right? Now, we could probably stop there, but could we add some more? What about S intersect T? What else? How about S union D? S union T. And I don't think I can use any complements because they're in both S and T, but I think that's a good list there. All right, it looks like it's time for you to practice. A little bit more challenging. You're going to have to use 3 different Venn diagram circles. So you'll be making, kind of like the 3 that overlap, and then the A is actually going to be our universal set on this next one. Let me pull that over and demonstrate that. All right, so what I'm talking about here is that this is actually going to be our universal set, it looks like. So go ahead, pause the video, do your best, answer the questions that go with it, and then we'll go. All right, let's see how you did. All right, I'm going to draw 3 circles here. I'm going to call this, we'll call this set B, this is C, and this is D. So it looks like the number 2 is in all 3, right? Is there any number that is just in two of the sets? Let's see here. B is 2, 4, 6, and 8. So 6 is in B and D, right? All right. Okay, I think that's it on that one. C has got 2, 3, 5, 7. So it's got the 2, and then 3, 5. Oh, I don't need the comma. That's not really necessary. 3, 5, and 7, right? Okay, and then let's see, over here on D, we had 1, 2, and 6. So I'm thinking just a 1 right here. But 1 wasn't in any other set, was it? No, it wasn't. Okay. And then we've got 2, 4, and 6. Now, B and C don't have anything in common, do they, besides 2? No. So I'm going to say 4 and 8 over here. Cool. What elements are in A union B? So remember, A is this universal set on the outside. I should probably show that as well. Oh, but was actually, you know what? There were some numbers that we didn't include here, right? Which numbers did I miss? I got 1, 2, 3, 4, 5, 6, 7, 8. I'm missing 9. The number 9. Okay, so A union B is everything that's in A union with B. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's everything that's in A. Now I got to add what's in B. But all the things that are in B are already in A because B is contained in A. So I'm done. What elements are in B intersect C intersect D? So it's the intersection of B and C. So the intersection of B and C is this little magnifying lens looking thing, right? That's the intersection of B and C. Now, where does that intersect with D? Well, that intersects with D right here. So that's the number 2. Do I have some more down there? Oh, and I got some old notes. Let me get rid of those. Okay, so now we're on to C union B intersect D. So C union B. All right, that's all that. Intersected with D. So that's anything that's in C and everything that's in B. So that's everything that's in C and everything that's in B and then intersecting with D. So it has to be in D. But it also has to be in either B or C. So that would be 2 or 6. So that's everything that is in B and C. B or C, excuse me, and in D. All right. Next, we're going to talk a little bit more about intervals. Describe the following number sets using set builder and interval notation. All right, so intervals are necessary to describe sets that have a cardinality that is infinite. So if I was going to say I want to describe this set A using discrete numbers, you might say, oh, okay, well, this set here that I've got, well, it's got the number 0, it's got 1, it's got 2, it's got 3, right? I mean, there we are listing them in set notation. That's a terrible curly bracket, but you get the idea. The problem is, so I'm missing a few numbers, right? I'm missing a half, 1.5, 2.5, 1 1/4, 2 1/4. I'm missing an infinite number of numbers because between any two integers, there's an infinite number of them. So we need another way to describe that. And unfortunately, the history of mathematics, they just never settled how they're going to do this. We've got to learn both. We got to learn interval notation. We got to learn set builder notation. So we're just going to practice them both. Okay. So set builder notation is a set, but we're going to be using building. So we're building the set. The way we build it is we're going to say, hey, I want you to include all of these things that meet this criteria. Okay. So I want this to be the set of all numbers. Yeah, usually we just call it X, such that 0 is less than or equal to X which is less than or equal to 3. Now, if I wanted to be really robust here, I would actually say all real numbers x such that. But since we're dealing with a domain that is implied to be the real numbers in this course, I'll leave that part out for now. Okay, so that's set builder notation. You may be more familiar with this part here than this x with a vertical pipe here. What is that saying? Well, I'm saying all x's such that. That's what this little thing here means. It's red. Such that, or with the condition that. Just say such that, okay? So it's x such that this condition is true. Now that's set builder notation. Notice this colored in circle here is saying that 0 is included. That's why I have the bar underneath, okay? That's why I have less than or equal to. Now let's do interval notation. Well, with interval notation, when we have a closed endpoint, which is what we call that closed, all right? A closed endpoint, we use a bracket. So a square bracket, 0, comma, 3. This interval is read to be simply all the numbers from 0 to 3. So you can see right away, interval notation is pretty easy to write, isn't it? But unfortunately, we need to learn both. We just must. Okay, let's go on to the next question. All right, notice that I have here a circle that's not filled in. This is called an open endpoint. Okay? So let's do our set builder. We have all x's such that 0 is less than x, which is less than 3. So we have the set of all x's with the requirement that x is greater than 0 and less than 3. Let's do that in interval notation. The open endpoint interval notation is indicated with the parenthesis. Now, there we go. Now, I know what you're thinking. We haven't actually started graphing stuff yet, but that looks a whole lot like x comma y, right? You have to use context clues in math. I'm sorry. You need to know that that's an interval, not the point x comma y, but I assure you it will always be very clear based on the situation that you're in. All right. Let's do a couple more. Like about, what, 4 more? And then you get the practice. All right. Okay, on this one, I've got set builder notation. I've got the set x such that x is greater than or equal to -1. Interval notation. Because there is no limit on this, right? So I just said x greater than. Note, I could have this in any order. I could have said -1 is less than or equal to x. You know, equally correct, just as long as it's true. All right, I'm going to say bracket -1. And then the closing interval here, what we use is the infinity symbol, which is like a sideways 8 if you haven't seen it. Now, infinity is always an open interval because infinity is not a real number that you actually obtain, take on, and stop at. So I want to make that very clear. Always parenthesis around positive or negative infinity. Okay? All right, let's do the next one. Set builder notation. So we use the set x such that this time the x's are smaller than a value, but they are not equal to. They are less than 2. And we'll use the interval notation. This time we're coming from negative infinity. So I'll say negative infinity, comma, 2. Now, the order of the interval notation matters. You have to put the small number than the big number. So please, if you have negative infinity, it has got to be the number on the left. If you've got positive infinity, it has to be the number on the right. All right, let's do another couple. All right, we got some kind of a little bit more interesting looking set here on this one, don't we? We got two parts. So let's see how that works. I've got the set of all x's such that -5 is less than or equal to x, and x is less than -2. So this is actually this AND operator. Let me take just a second there and tell you about it. We have two operators that we're using here, AND and OR. Now, if I say something like 2 is less than x, and let's say I said and x is less than 5. Actually, you know what? I'll use the numbers that I have in this problem here. So that's what I'm saying, right? I'm saying to be in this little region here, you have to say that x has to be greater than -5, and at the same time, you have to be less than -2. That's what and means. And is it's your intersect. In reality, it's your intersect, okay? So we're saying that has to be the case. There's also the OR operator. Now, the OR operator, you can't squeeze that together. With the AND operator, as long as the condition in the middle is the same thing, I can squeeze them together and say this: -5 less than or equal to x less than -2, which is exactly what I did. But if you have OR, you can't do that. You just have to separate them with the word OR. So I'll say OR 1 is less than or equal to x less than or equal to 4. All right, now sometimes people will put in this OR symbol here, you'll actually see people use a symbol similar to the intersect symbol. You'll see like an upside down V. Sometimes people actually use the intersect symbol. For me, it's a matter of personal choice. You can, as long as you're right, I don't care what you put. I'll use OR when using the set builder notation, and you'll see that I'll use the union symbol when doing interval notation. So for the interval notation, I have a square bracket because we're closed at -5 to -2. And then I'll say union 1, 4. Oh no, I forgot to make those square brackets. I was using open. There we go. All right, we got what looks like one more example here. All right, set builder notation. Well, you can just say all real numbers. And notice I don't put that in set builder notation because that is a set. It already is a set. You might occasionally see this in set builder notation. You'll say x such that x is an element of the real numbers. And that E symbol there, we'll talk about it later. That E means is an element of or is a member of. But for a problem like that, it's a lot easier. Just go ahead and stick with just putting the double strike R. And then on interval notation, it's -infinity to infinity. All right, you now have some practice problems to do. 4 of them. Please take your time, do the best you can, and then pause the video, do the problems, and then we'll get back together and talk about it. All right, let's see how you did. All right, this was letter A. I kind of lost my letter there. Okay, in set builder notation, you should have that we're looking for the set of x's such that, hold on. Such that x is greater than -2 and less than or equal to 1, which in interval notation looks like this. -2 with a parenthesis, 1 with a square bracket. All right, on this one here, you should said the set of x's, and you could really use any letter besides x, but since it's going horizontally, makes sense to use x, right? Set x is less than -3, or 0 is less than x is less than 3. In interval notation, we're coming from -infinity to -3, union 0 to +3. All right, let's take a look at this one. We have the set x's such that x is less than or equal to 2. How does that look in interval notation? We have everything from -infinity to 2. All right, on this one here, we have the set of x's such that x is greater than 0. What's it look like in interval notation? We have a parenthesis at 0 and always an open parenthesis around infinity. All right, another practice set. So pause the video and give it a try. And that's practice 4.4, and then unpause it and we'll go over them. Okay, let's see how we did. We're going to convert the following sets from set builder to interval notation. Okay. I'll use blue to, there we go. So in interval notation, this is all values of x that are greater than 0 and less than 8, but not including, so it's 0 to 8. Here, this is the set of all x's where -2 is greater than or equal to x, so the x's are smaller than that. So it should be -infinity to -2 with a bracket. So be careful on that. Don't trust the order of these inequalities. You know, if you need to, flip it around. All right, this is -infinity to 10. And with parenthesis there. And then I've got, let's see here, this is -infinity to 2, union 8 to infinity. All right, and this one here is a square bracket at -10 and a square bracket at 2. All right. Last thing you need to do before your exit ticket is you need to do practice 4.5. So pause the video. You know the drill. Pause it. Make sure you give it your best shot. Take your time. Unpause it when you're ready, and we'll go over it. Okay, for 4.5a, to convert this to set notation, I'll say x such that 1 is less than or equal to x, which is less than 2. For this one here, I'll say x such that x is less than 5. And for this one here, we've got x such that x is greater than or equal to 2. All right, for your little parting challenge, I want you to graph a set of numbers that are greater than 2. Describe the set with interval notation and set builder. All right, until next time, good luck on your homework assignment over this lesson, and I'll see you then.